so my name is Karina Rodriguez. I come from the University of Brighton. I am a DRI user myself. I'm a researcher. I am a computer scientist. And I work in the intersection between computer science and the arts and humanities. But I'm not an arts and humanities scholar. So I wanted today to introduce you to two users from that community. And before I do that, I wanted to introduce to you our project and how do I get to know these users. So the digital skills in the arts and humanity is, I will tell you the funding in a minute, but it aims to identify and develop innovative use cases and user journeys for DRI. And he thought it was very relevant. So when I got an email saying, does anybody knows any users? I thought, yes, we have a project that is related to that, and we can bring or invite two of our fellows to come and talk about their experiences. And the DISKAH aims to build capacity and collaboration among arts and humanities researchers to promote the adoption of DRI, right? So this is about these processes. The project itself is funded by UK DRI, no surprise, right? And it was part of the call to broaden access to DRI and skills, and is running from last year, November, and it will run until March 2027. And what we did in this project was to implement a fellowship program. So what we thought, and it is a network I will show you in a minute, but what we thought it would be a really good way to get users will be to develop a competitive call in which we will recruit through established criteria and a process for selecting the projects, 12 fellows that will bring potentially interesting use cases of DRI. So the call is open to academics in higher education institutions, but also I mentioned yesterday about the galleries, libraries, archives, and museums. Actually, these are recognized by HRC as independent research organizations, and they can apply for funding. So our call is open to academics, researchers or practitioners in the GLAM, or RTPs, right? So research and technical professionals. And what we really look in the project when we look at the application is what we call readiness. How ready these researchers are to leverage the opportunities that DRI can offer them. So we look at readiness to scale up existing software workflows. And I mentioned maybe yesterday during my presentation that because a lot of the research that happens in the arts and humanities looks at culture, and it can be material culture, it can also be intangible culture. There are many times data sets in institutions that they look at. So you tend to find large-scale data sets when they are looking at a collection or an archive, and you'll see examples of this in the projects you will see in a minute. Okay, so what the fellowship involved, and again, you will get maybe a sense when you see the presentation, but we will select up to 12 fellows. So there are 12 use cases, 12 user journeys. Also really 12 interesting people to understand where they, what is their career path. And what we do is we fund 10% of their time so that they can be released from teaching or other research activities. And we look at three elements. One is professional development. So we provide them with training, and we have a syllabus of skills that they ask or request about enabling them to access the digital research infrastructure. And we also do networking. So this event for us is a good opportunity for them to meet the wider research community, not only the arts and humanities community. And we do an element of leadership because part of their fellowship involved them training others. And that's interesting because when it comes to infrastructure, they also need to think how other people are going to be doing what they are doing or accessing what they are using for the research, right? So they have to think about how do they bring others. And we do this to maximize the impact of these fellowships. Okay, so I show you here the network. So we are 3 co-leads. So we have University of Brighton, Exeter, Eamon Bell is here. Yeah, Eamon, he's co-leading the project, and UAL. And then we have other partners and our fellows institutions. So this is our initial network. And of course, we will expand it in the next year with recruit more fellows. Okay, there are we have these 5 projects, and today I would like to present for you 2 of them. As you will see, we go from music to what we have Brian, polygraphs, but we also have things that are about OCR, so text recognition or modernism, and we have something about text, there is a lot of digital humanities about understanding text to natural language processing. Okay, so shall we start with Jasper? So Jasper will talk to you about music now.
Good afternoon, everyone. One of the parts of the call asks for non-traditional HPC users, and I think as a performing pianist, I'm probably one of the more non-traditional users. I'm going to talk about our project, which is hosted at the Guildhall School of Music and Drama. Now, Guildhall School of Music and Drama is a great place to be if you're a performer, but if you're using any form of compute, maybe not the best place, but we'll get into that later. First, a little bit about our guy, our man, Domenico Scarlatti. Now, who was he? He was one of the great keyboard composers of the Baroque era. He was born in the same year as Bach and Handel. And he was extremely popular across Europe, so popular, in fact, that in London they had a Scarlatti sect, and some people even called it a Scarlatti cult. Now, despite this, we know almost nothing about who he actually was. We know he was the music master, teacher of the Infanta Maria Barbara and later Queen of Spain, Maria Barbara, during most of his life. But he appears to have spent half his life in royal music quarters in Madrid, but his music went viral across Europe. And how did that happen? Over the last 3 years, I've worked as a PDRA on the Texan Scarlatti project, which is funded by the Leverhulme Trust and Research England. And this project has generated data of what I would say a relatively large scale in musicology, consisting of around 190,000 musical variants in nearly 3,300 manuscript and printed copies of Scarlatti's keyboard music. Now, this is the result of over 10,000 hours of skilled work by about 40 different people. And of these 3,300 copies, not one is in Scarlatti's own hands. So we don't have a single autograph, as far as we know, which makes his music a particularly interesting case study. Now, we think we are the first musicological project to apply computational phylogenetics at scale. I believe so. And we think this will transform our understanding of the transmission of Scarlatti's music through simple scripts all the way to potential high-performance computing use. Now, we aim to chart the transmission and reception of Scarlatti's keyboard music by establishing the stemma of all surviving 18th century sources and by mapping the major routes of transmission, circulation, and their implied chronologies. Now, this involves detailed collation, comparison of all extant copies, which is a process that cannot be automated currently. So Texan Scarlatti combines traditional textual criticism with computerized data analysis, management, as well as citizen science. Now, why phylogenetics? These methods have been used in many studies to understand the transmission history of literary works, and recently they've also been applied in musicology to interesting proof of concept studies by Windrum and Howe at Cambridge in collaboration with musicians such as Terence Charleston and Yota Mita. Now, their studies show that the results of phylogenetic analyses align closely with traditional findings. While innovative and interesting, they focus only on one or two pieces, and we're focusing on 560 pieces, so the scale is slightly different. And it seems from what they told us in Cambridge that the transition from a musicological data set to Nexus files, which are compatible with phylogenetic software, was a significant hurdle. Now, we think phylogenetics could help solve the Scarlatti jigsaw puzzle, which is a puzzle with over 3,300 pieces. We don't have a picture, and from which we can assume as many, if not more, pieces are actually missing. And we think this computational approach will allow us to answer essential questions, such as which manuscripts and printed editions form distinct family groups, what were the major routes of transmission across Europe. And at the same time, we think this approach will provide us with new questions about the importance of individual musical variants. And we hope to cross-validate these results against known historical relationships and use them to further support these or to propose new theories of transmission. And today I'm going to speak a little bit about that. Now, over the last 3 years, we've been busy comparing all witnesses available to us in our own notation system, which you can see on the slide here. So typical variant recording here speaks to the position and pitch of a note in control, and then what actually happens in the witness. And these are entered on worksheets by research assistants using Google Sheets. We think they're easy to use. Basically, everyone has used spreadsheets before, so they probably know how to populate one. All they need to do is know how to read music and then follow our preset template. Now, after the collations are finished, they are validated by a different person to ensure accuracy. Now, the result of these validations is something like what we see here at the top in red. We've got our header section, which is just a bit of metadata about the sources in question. Then in green, we've got what we call the bar section with 1 row per bar in a particular musical source. And then at the right side, we've got a little bit of information about modern editions. So where would we find a modern edition of this particular piece? But our results aren't always as tidy as this. So this is a bit of a mess from K112, and the reason for this is that the original source, the baseline control that we used, which was as close to Scarlatti as we think is possible, actually has this entire piece written in demi-semiquavers, 30-second notes. So you can see almost every single bar there has something to do with the number 16, which means that the demi-semiquavers were actually turned into semiquavers in these copies. Potentially, that might be an interesting musical variant, but maybe not. So we think that organizing and analyzing these, by computer scripts and software is probably the way forward. So short summary of the tools involved. We have a tool called Rosengrave, which is named after one of the main Scolati people in the 18th century, which essentially just makes the spreadsheets and pulls data from them. So just using Google API. We've got phylogenetic software. So far, we've been using Popstar and Splitstree. And then I've written most of the code in Python to generate matrices like these, which essentially tell us here at the top, you've got a bunch of zeros. That's just the baseline. We don't actually write anything about the baseline. And then all the sources there on the left side and their particular variants. You see quite a lot of number nines. That will probably refer to a category. I don't know off the top of my head which one that is for this particular piece, but you can see quite a lot of it lines up. So that might mean that they're related in some way. Essentially, the way it works, to be able to use our data with phylogenetic software, we use a dictionary that holds all our possible variant notations, just using regular expressions, to translate our categories into the nexus identifiers here. So the results can be seen in that example, as we just saw. Once we use phylogenetic software then to analyze these, we can come up with various visualizations, and which may suggest certain types of kinship. So one source there, the second one, Berlin, that's actually a source which we thought had disappeared, but actually turns out it was still in the archive all this time. And we have found that that source is actually quite close related to sources which are in Vienna. And a colleague of mine based in Paris, who I've been in contact with recently, found that one of these scholars in the 19th century working on these sources he went to Berlin. He said, I actually don't need anything from Berlin because I have everything I need in Vienna. So now we know that these sources were probably related. They may have been copied from each other or may have stemmed from the same model. Now, what are our next steps? Much of our work is text-based, and the use of concise and mostly alphanumeric code means that most of the conversion steps are very fast. So we don't actually need HPC. However, if we were to extensively test our findings of a piece, this takes a few minutes. But from earlier research, we know that Scolati's pieces traveled in pairs, in triptychs, in other organizations. And so it appears that at some point he began composing these pieces as, partners, pairs, triplets. Now, especially data-heavy pieces, as well as certain smaller groupings, would take a lot longer to compute. And considering we've got about 560 individual pieces, you can see that this is an important consideration. Now, since one of our goals is to make these types of analyses available to anyone, not just us, as part of the DISKAH Fellowship, I developed several collab pages, and these pages allow anyone to dissect our data. So I made some collab pages which allow anyone to dissect our data set. They can analyze individual sonatas. They can develop their own bespoke weighting if they wish to disregard certain variants in their analysis. So we give the power to them, essentially, and they can then use these weighting nexus files, which again are compatible with phylogenetic software. But this is all largely achievable on a laptop. But access to a cluster might inform or transform the approach we have taken in the following ways. Firstly, as I said, it would allow us to scale up the complexity of the operations. And since we're also looking at the different organizations, that would be a lot easier for us to do. And we also think they could be used to create advanced visualizations of the complex stematic relationships, which makes them more accessible to non-specialists. Now, I'm coming to the DISKAH Fellowship from an unusual background. As I said, I trained as a performing musician. I played all the canonical repertoire, Bach, Beethoven, Mozart for the modern piano. My doctorate was on the piano performance of Bach's keyboard music, and the Scolati project is an even earlier material, mostly from the 18th century. Now, before starting the fellowship, I had a little bit of programming experience, not too much, but absolutely zero experience with HPC. So I have enjoyed learning and expanding my skill set, as I'm keen to approach our dataset from many different angles. But I have found the best approach for me is combining this passion for digital desk work with, as you can see from the photograph here, some traditional fieldwork in Italian archives. Thank you.
Okay, so now we'll go to Professor Brian Bull, presenting the project Polygraphs.
Good. So I think, like Jasper, I'm a somewhat usual user of HPC. In particular, I'm a philosopher by training, and I think philosophers on the whole have utilized compute facilities. I want to tell you about polygraphs a bit, about the project as a kind of use case, and then articulate a couple of sticking points that I've had in case they resonate or are useful information about what a user with my kind of background might experience engaging with HPC. So polygraphs kind of an apex award from the Royal Society. and others. And I say with Alexandros Koliousis and Mike Pesey, we built a computational framework for philosophical simulations. In fact, of course, Alex, the framework. It's a framework, as I say, for philosophical simulations in social epistemology, which is to say knowledge in groups, basically in communities. And the Python code's now available on GitHub, and we've begun to use it to investigate models of individual and collective rationality and the effects of mis and disinformation in communities whose information sharing practices are structured in different ways and who also pursue various individual information processing strategies, or slightly different variant models of what it would be to rationally process information. We've got some assumptions that I think are worth mentioning. So our models, which come ultimately from economics, but then were adapted for philosophy of science and then to the study of misinformation, idealize away from certain aspects of the real world phenomena that we're looking at. In particular, we abstract away from any psychological biases that the individual agents may exhibit, and that really allows us to identify alternative causes of ill effects of mis and disinformation, in particular structural causes and informational environment themselves. And the bad outcomes here can be in the form of inefficiency or inaccuracy, right? The community can get the wrong answer to the question that they have, or they can just take a long time to get there, to get the true answer. Our dependent variables concern degrees of belief individuals have in a salient truth. They're pretty simple agents. They just care about one thing, this one truth. And the emergent phenomenon as well of the collective opinion concerning that truth within the community. While we use statistical methods, actually our arguments are largely qualitative, and the research aims to be interpretive and normative in character, right? What ought rational agents to do, for example, in response to information. And at the same time, we employ general models and aim at uncovering widely applicable causes. And so our work, I've argued, differs from much that's done in the digital humanities and also work in the computational social sciences, and I think of it as computational humanities work. So the Apex Award came with a small public engagement side award as well, and we worked with colleagues at Northeastern University's Center for Design to physicalize our data, and hopefully you can click on that link to just show you some of the animations that they produced, which illustrate what's known as the Zollman effect. This is the finding that in small networks, and I emphasize small, Kevin Zollman was looking at networks of about 10 nodes, right? 10 agents, very small communities. There's a trade-off between accuracy and efficiency. Right, you can see the agents are sending information to one another. Thank you very much. And here we have a well-connected network, complete network. On the other side, a less well-connected network. The less well-connected network gets to the true blue opinion, though it takes them longer to do it. Yeah, and it's worth emphasizing that, of course, both accuracy and efficiency are kind of important in communal investigations, right? If you think about public debate around what to do regarding climate change, there's some timeliness to this, as well as an importance of accuracy. So I've had some follow-on funding from the British Academy under a talent development award with a network scientist to develop some materials to teach humanities and social science researchers both how to use graph computing in their research and why they might want to do that. We built a public-facing Canvas page to share those materials. And I also got some internal funding from Northeastern to work with my colleagues in philosophy and in English to investigate the relationship between this lady, Margaret Cavendish, and the Royal Society, using more the kind of philosophy of science model that we have than the misinformation one. We did this in part because Cavendish is known to have visited the Royal Society back in 1666, even though women weren't made members of the Royal Society until 1945. So she was a kind of early character to have engaged with the infrastructure of science, I guess. Yet she's marginalized, right? She's not a member of the society. So with some student research assistants, we've run simulations that suggested had she had better connections with society members, not only might she have benefited personally, epistemically, right, arriving at the truth more quickly, but so too might the society as a whole. So you can see on the top, we read this is like how long the simulation runs for, the number of steps, the distribution across all the sims that we've run, and when she is connected to all the members of the Royal Society. On average, the simulations arrive at the truth more quickly than when she is merely connected to the people that in our data set she's already connected with. The DISKAH project itself, I think of as enabling me to take kind of greater control of the computational aspects of my research. And that's meant, on the one hand, improving my own Python skills, but also handling more of the kind of polygraphs workflow in a high performance computing context. As for my own Python skills, I have gotten better over the course of the 6 months that I've been working on this. I'm able to run, for example, community detection algorithms on, in this case, the data set that we use on the Cavendish project. This is a graph representation of early modern figures in Britain called 6 Degrees of Francis Bacon, which I love as a name. That's not our name. And so you can see here there's basically 3 large communities detected and a bunch of small ones. And yeah, not only are there algorithmically detectable communities, there's actually labeled groups within the data set, including the Royal Society, which is nice. So working with a graduate research assistant, I've been able to produce visualizations like this one. And here we get effectively, as the steps of the simulation go along, how confident are the various communities in the truth, and we can plot out the mean credence or mean degree of belief for all the nodes in the network, and for each of those subcommunities that were algorithmically detected. And for the Royal Society itself, in red, you can see the Royal Society, as it happens, does a little better than other communities in this case. As for the second part, the kind of HPC experience, so we are running our simulations on much larger networks than others that practice computational philosophy. I mentioned Red Zolman's experiments were on 10-node networks. The Francis Bacon network is like 13,000 nodes, and of course we can scale beyond that. We also need to run quite a large number of simulations for experiments to get statistically significant results. And so Polygraphs has actually made use of the discovery cluster on the Massachusetts Green High Performance Computing Center from quite early on, probably 2022, I think we started doing that. And as I'm now aiming to manage the workflow of the project more kind of autonomously, meaning independently of my computer science and data science colleagues, I basically have found a couple of sticking points that are connected with, on the one hand, the virtual environment in which I run my simulations, and on the other hand, the management of my synthetic data that is the output. So on the virtual environment, as it turns out, just to give a little texture, Polygraphs is built on a library called the Deep Graph Learning Library that runs on PyTorch. And sadly, and I say sadly, more almost annoyingly, Conda can't be used to manage the dependencies in this case, because DGL has stopped updating its communication with Conda. And so that has meant that the installation of Polygraphs code is a little trickier than I would have hoped. And I recently managed to migrate from the Discovery cluster, as it's nearing the end of its life, to our new Explorer cluster. But I had to recruit my colleague to manually manage the dependencies and install compatible versions of the various software packages needed. And it's been suggested to me by colleagues in research computing I might containerize my code to put it onto Bead, for example. I'm not sure that's going to be the right solution, because we will update Polygraphs code over time, and I want to be able to update the environment that I'm working in accordingly. And in this problem, but a collaborator in Australia, they're going to want to set up the code there as well. And from what I gathered, different clusters are going to have different background packages in place. So it's, for me at least, a non-trivial problem to resolve. And then the other issue was surrounded data management. I run my larger experiments on the high-performing computing cluster, but some of my collaborators, my PhD student, run their simulations elsewhere. Maybe sometimes I want to do some simulations just locally on my laptop as well. So I recently set up a shared data storage space on the HPC. I think it's 18 terabytes, which is enough space for us now, at least. But as I say, it's sometimes convenient to work locally on the laptop, for example, for data analysis. So we've been kind of uploading and downloading data, dumping it into a Google Drive and things like this. And that is not only a little poor, but it's also we run the risk of actually duplicating our data and skewing our statistics by doing that. So we've heard a bunch about Globus today. I have been told that Globus can help me to sync my data across my local machine with the data on the HPC, and to manage permissions if I end up using more sensitive data down the line. I've begun to explore that. I haven't managed to get it working for me just yet, but I guess this is an issue that this community may be already aware of. So I'll stop there, and thanks very much.